Hey guys, this is me, Mr. Wee again. We're going to continue from our last notes. I think we left off with a proof with segment addition postulates. So we're going to kind of go off of that and go on to some other examples. Let me see if I can move this a little bit. Okay. So this next kind of subtopic that we're going to talk about is a proof using segment congruence. When we're talking about segments being congruent to each other. And then we're going to draw sort of like a symmetrical V. And then at the midpoint of each of these lines, we're going to draw a point X, Z. The point at which the lines start is Y. And the outer points of this kind of V structure is an F and S. And then here's what's given to you. X is the midpoint, so it is verified. It's the midpoint of SY. And Z is also the midpoint of YF. XY is equal to YZ. And then what we need to prove that ZF is equal or is congruent to SX. All right, so again, all we know so far is that X is the midpoint here and Z is the midpoint for this line. That's it. It doesn't tell us anything about what this measure of SX is equal to. It doesn't tell us about XY. It doesn't tell us anything about the length of these guys. All it particularly says is that X is the midpoint. That's it. And then also, actually it does. I'm sorry. XY is also equal to YZ. So let's kind of make that into a thing. Okay. Ultimately, we need to prove that ZF, this guy, is congruent to this guy over here. Those two line segments are congruent. And all we know so far is that's the midpoint, that's a midpoint, and then these two are congruent. Okay, so let's build an argument into how to approach this. Already in my head, let's think of a few things. The midpoint theorem would say that this and this are equal. The midpoint of this guy would say this and this are equal. Okay, ZF and XY are equal. And then we know that because ZF is congruent to YZ, right? Because that's the midpoint. We also know that this being equal to this, that means ZF is also equal to XY. And also, because ZF is equal to XY, we also know that SX is equal to XY. So guess what? This and this should be equal. But now we need to kind of organize our thoughts into this table, right? So it's kind of nice. It kind of gives organization to one's thoughts. Though it is, for many people, tedious. It's a lot of different steps. But just like in English or in any other subject where you have to write out things, okay, you need to be clear and communicating what you know. It's really important that you do that, or else you're just going to have a jumbled mess of information talking from one person to the next. That sounds great, but sometimes you can't do that. You need an email, or you need a, like sending documents or reports, right? You need to communicate through different ways. Writing, right? Speaking, I think we're all pretty good at, or we can get better at, but we're all fairly decent at. It's the writing aspect that we need help on, right? Or we're trying to work on. So that's why we do school. Okay. Sorry to get kind of philosophical, but not really. Not too philosophical there, but sorry to get into that point. Okay. So we do have to kind of make it very explicit. So again, this is very explicit communication. This is just a practice in communication in math, if you think about it. X is the midpoint of SY. Z is the midpoint of YF. Okay. And we do know that XY is equal to YZ. Okay, so I know that. Okay, so like I said, if X is the midpoint, SX and XY are going to be congruent to each other. If you look at the definition of congruence, or I'm sorry, not the definition of a midpoint. It will explicitly say the definition of a midpoint. I mean, go back into your cheat sheets that I gave you, where I handed out. XY. Sorry about that. Your cheat sheet should say if there's a midpoint, there are two segments made from that midpoint that are congruent to each other. Okay. Also, kind of to piggyback on this, I could write in the same line that because Z is the midpoint of YF, YZ and ZF are congruent to each other. YZ and ZF are also congruent to each other. So here's one step in your book that I will make explicit that I'm not a huge fan of, but they do say because the given statement is XY is equal to YZ, you can also say that XY, the line segment, is congruent in shape to YZ. Now, you know me, what I say is when you're congruent, you know you're equal to. But that does not necessarily mean that if you're equal in measure of something to each other that you're completely congruent. Just like twins. If you are a perfect twin to someone else, you are congruent in shape and you measure the same in weight, height, whatever, right? But here, that's not necessarily true. You could say two people weigh the same, but they do not look the same and they're not shaped the same. So I like saying that if you're congruent, by the definition of congruence, you are equal. But it's really hard for me to see that if you're equal, you can also be congruent. Okay, so this is what this argument is saying. So they're saying that because xy is equal to yz, these two are congruent by the definition of congruence. I don't necessarily agree with that. But we are, for the sake of kind of keeping consistent with your book, we are going to say that, okay? I just wish it was kind of, this problem was set up to be flipped around where the given statement was that XY is congruent to YZ, okay? But we are going off of your book, so it is kind of consistent with what you're doing in your problems. But please keep that in mind. Always, always keep that in mind. Okay. The next thing is, let's take a look at what we have. We have xy is equal to y, or sx is equal to xy. yz is also equal to zf. If you look over here, you have sx is equal to xy. Xy is also equal to yz. Sx is going to be congruent to yz. Again, sx is equal to xy, xy is equal to yz. Therefore, sx is equal to yz because of the transitive property of congruence. So let me stop for 1 second. I know this is a very long example, but I need to kind of find the cheat sheet here that I have, so you know where I'm pulling this from. So just letting you know, the definition of the midpoint is from 5.1. Okay, that should be in section 5.1 right here, the definition of a midpoint. So it says if these two, if you have a point there in the middle, then these two lines are going to be congruent to each other. Also, if the two segments have the same measure, they're congruent. Oh, so I do see that now. If they have the same measure, which is right here. So if they have the same measure, then they are congruent. That's what this is saying. But like I said, I technically don't see it that way, but it's okay. All right. So I guess by their definition that they provided, that should be good then. If these two are equal to each other in measure, then they are also going to be congruent. So I guess technically by the rules stated here, that works. I mean, this works. This is equal to each other. That makes these congruent. But like I said, I always think differently in terms of, I differ in that. Okay. Okay. Let's see. Whoop. Okay. And then here for the transitive property, I grabbed it from 5.2. We have a bunch of different things of equality, and since we're dealing with, so this is addition property of equality, this is subtraction property of equality, right? These are all things that you've already done before. Just keep in mind that transitive property of equality, that is of equality, we are dealing with congruence, so we do have to say that this is specifically transitive property of congruence, which does exist. It's the same thing, but it talks about congruence. If two things are congruent, if this is congruent to this and this is congruent to this, then this must mean that this is congruent to this. We just have to say that's congruent. Okay, sorry for taking so much time to solve this. Okay, also, let's see, what else can we say? Also, another thing is if this was congruent to this, YZ is also congruent to ZF. So that means SX is congruent, XX is congruent to ZF. Again, that is another transitive property of congruence. All right, and if we want to be technical here, the original statement that you're trying to prove is ZF is congruent to SX. And what we have here is SX is congruent to ZF. If we switch the positions, it's still the same, but written a little bit differently in order. You don't have to have this step, but I call this, or I don't call it, but it's called the symmetric property. Specifically just symmetric property, but since we're dealing with congruence, we have to say it's congruence. And where did I find that? Where is the source of that? That should be in 5-2 in your cheat sheet or in your book, symmetric property of equality, but be very careful. We're not dealing with statements of equality, we're dealing with statements of congruence. So this is defined by the symmetric property of congruence. All right, guys, we will continue on with one more example from this section very soon. Thank you very much. Goodbye. Okay, go ahead.
Mr. Reed?
Yeah.
So last